Section 2.1, represent relations and functions. A relation is a mapping or pairing of input values with output values. The domain is the set of the input values, or x values when we talk about our xy coordinate plane. The range is a set of output values, or the y values when we talk about the xy coordinate plane. In example number 4, we have to identify the domain and range and then represent the relation using both a graph and a mapping diagram. So we're given this list of ordered pairs. To find or list the domain of those ordered pairs, we're simply taking the x values out of those ordered pairs and writing them as a list. And when you write that list, there's a couple of things that you need to keep in mind. You need to make this list from least to greatest. And if there are any repeat values, you do not write them multiple times. You only write the value once. So for the domain, if I take all the x values out of those given ordered pairs and list them in order from smallest to biggest or least to greatest, you would have -2, -1, +1, +2, +3. It's the same idea for the range, except now instead of the x coordinates, you need to use the y coordinates. Same rule applies where you list from least to greatest and you do not list any values more than once. So the range for this relation would be -3, -2, 1, and 3. So again, we have to represent this relation using a graph. That simply means we have to graph these 5 points. So very quickly we could do that. I have them already done for us here. Remembering the x coordinate is the horizontal coordinate, the y coordinate is the vertical one. The x coordinate comes first in an ordered pair, the y coordinate is second. So you move left or right initially from the origin, then up or down to locate those points. The next representation we have to use is called a mapping diagram. So a mapping diagram can be laid out similar to this, and you actually don't even need to draw these shapes. You could just make these lists, and within each list, input and output, we put those same values that we listed for our domain for the input and our range for the output. And notice again, I've listed them in order. This is just going to make life easier. And I have not included any repeats. Then to complete your mapping diagram, you draw an arrow from the input value to its corresponding output value. So in the first ordered pair we were given, -2 is the input, -3 is its corresponding output. I would draw an arrow between those two values. And I would repeat that process for the remaining 4 ordered pairs. So the mapping diagram would look like this when it's completed. Now, a relation could possibly be a function. A function is a specific relation where each input has exactly one output. So using that definition, is this this last example a function? Does each input have only an arrow to one output? This one would be yes, this is a function because each x value has only one y value. So again, the same type of question, tell whether each relation shown in these mapping diagrams is a function and be able to write a short explanation as to why or why not. So the example in part A, is this a function? This is a function because each input has exactly one output, or each x value has only one y value. Is the example in part B a function? This is not a function because the input value of 1 is mapped to two output values, two different output values. If it were a function, it could only be mapped to one output. So with a graphic representation, we have to be able to tell the same thing. We have to be able to tell if a relation is a function. To do that, we use the vertical line test. You know a relation is a function if and only if no vertical line intersects the graph at more than one point. So to demonstrate this, I've got a vertical line here, and this first graph on the left, that's a relation because it's graphed. It's one of the ways of representing it. If I take this vertical line and I move it across this graph, at any point, does it touch, or at any time rather, does it touch that graph at more than one point? This does not. So that means it passes the vertical line test, which means this does show a function. If I do our second graph, pass this vertical line through this entire graph, is this relation a function? This one is not a function because there are actually an infinite number of places where this vertical line intersects more than one point at a time. Does this third graph represent a function? This third graph, I get 2 points hit right there. That's enough to say that it's not a function. I even would have 2 points hit at the same time over here. But all it takes is one instance of that vertical line intersecting 2 points at a time for it to not be a function because it fails the vertical line test. Linear equations are any equation that can be written in the form y equals mx plus b. Hopefully that looks familiar. That's called slope-intercept form. A nonlinear equation is an equation that cannot be written in that slope-intercept form, y equals mx plus b. And then at times, when we talk about functions, we use something called function notation, which means instead of using the variable y, you instead use something that looks like this. This is function notation, and it stands for f of x. That's how you would read it, f of x. And you could change that to any letter. G of x is used a lot. H of x is used quite a bit. But again, it means the exact same thing as y. It's your output. X is your input. So when you're told to evaluate, this goes back to earlier this year and even back to Algebra 1. When you're told to evaluate, you take your given equation. Here we have one just written in slope-intercept form. So we know that it's linear. And what we have to do to evaluate is first we have to substitute the value that we're given. So I take 2 and I substitute it for the x variable. Then we just follow order of operations to simplify, and we get y equals 14. The example on the right, this is also a linear equation or a linear function. This one now is just written in function notation. I've taken out the y, replaced it with f of x. Notice the right side is still slope-intercept form. So this is still slope-intercept form for a line. Again, it's just using function notation instead of the variable y. You would you would evaluate this the exact same way. The notation changes just slightly. Now, anywhere you see an x, you would plug it to. So technically, when using function notation, you're showing that it's a 2 that you plugged in. That's the whole purpose on the left-hand side here, because it shows the input right away. And here's the work. And then when you actually evaluate it, it's still showing the input. That's why some people like to use function notation. You can see the input and the output at the same time when you write using function notation. So now, tell whether this function is linear and then evaluate it for f of 2. So the function that you're given is f of x equals x minus 1 minus x cubed. Is that a linear function? This is not a linear function because of the exponent of 3. Remember, just above in your notes, linear functions or linear equations have to be able to be written in the form y equals mx plus b. There is no exponent of 3 in that form, so this would not be linear. Now evaluate f of 2. When it's written using this function notation, that's telling you that 2 is the value that you need to plug in for your x variables in your function rule that you're given, your equation. So when you're evaluating, like we said before, the first step is to substitute the value in for your variable. Then you follow order of operations. So we have to take care of that exponent of 3. And then we would have f of 2 equals -7 when we evaluate. Here's some terms that should look familiar to us. X-intercept and y-intercept. X-intercept is the point where the graph intersects or crosses the x-axis. Keep in mind, anywhere along that x-axis, the y value is a 0. So any x-intercept, the y value in that ordered pair is going to be a 0 as well. The y-intercept is the point where the graph intersects or crosses the y-axis, meaning that the x value, the x coordinate for any y-intercept is always 0. Now to graph at this point, we're going to ask you to use the x and y intercepts and one other point in a quick table. If you are doing this and you just want to make a T-chart, that works instead of drawing a full table like this. So let's say I want to do the y-intercept first. If I'm going to find the y-intercept first, that means I need to plug 0 in for x. So I'd take 5 times 0 minus 3 to figure out my y value. Just simplifying this, we would find that we'd have a y value of -3. So the point 0, -3 is our y-intercept. Next would be to find our x-intercept. That means the y value has to be 0. So I plug 0 in for the y in our original equation, and I solve for the remaining x variable. And that would give me 3/5. And now for the third point, all we have to do is pick an x value and substitute that in to our original equation. We can pick any x value except for 0 and 3/5. Can't use either one of these that we already have. So if I just pick an easy one like 1 and I plug that in, 5 times 1 minus 3 gives me a +2. Now again, each of these rows in this table is an ordered pair. So we graph those like we did earlier. And then I recommend that you use a straight edge to connect those. Just makes your graph a little bit more accurate and neat. And this is what it should look like. Our second graph that we have to make, we're going to follow the same process. We can find our y-intercept first. Realistically, you could find your x-intercept first if you wanted to, but I like finding my y-intercept first. Just makes x equals 0 right away. Solving that, 1/2 times 0 plus 2 gives me 2. Now I can find my x-intercept, and I know that's when I have to let the y value be 0. So if I plug 0 in for y and then solve, I'd have to subtract the 2 and then multiply by the reciprocal of 1/2, and that reciprocal is 2. So if I subtracted the 2, I'd have -2. Multiply by 2, which again is the reciprocal, I get -4 for my x coordinate. And now I get to pick my next x value, but I'm going to be smart about my choice here, because if I look at my equation, I know that I have to take that x value, multiply it by 1/2. And instead of making myself deal with fractions or decimals, I'd rather have whole numbers or integers. So I'm going to be intelligent about my choice, and I'm going to use an x value that's easily multiplied by a half or divided by 2 if you want to think of it that way. So using just +2, I could use +4. I could use -2. Anything that's an even number would be a choice that you would probably want to make for this one. So now plugging that x value in and simplifying, we end up with +3. So again, we have to take and graph those 3 points and then connect them with a straight edge. And that's what our line should look like on our graph. Our last example takes the idea of domain and range and whether or not a relation is a function and shows it in another representation instead of a graph or a mapping diagram. This is now shown using a table. From that table, though, you should be able to tell what the domain and range of this relation are, given that you're told the year that the bridge was completed is your x value or your input, and the length of the bridge is the y value or your output. So keeping that in mind, the domain is our input values. We would take these years and we'd list these in numerical order, least to greatest, not repeating. And there aren't any repeats in that. So we do have to list all those values, just making sure we put them in numerical order, makes them nice and organized and easy to work with. And the range would then be your y values or your outputs. This time you do have to look out because you do have 2 of the same values, and we have to remember we don't want to list that value more than once. So now part B asks the question, is the relation in part A, so using that domain and range, a function? This is a function because each of those inputs has exactly one output. Now C, if you flipped it around, if you took the length as the input and the year as the output, would that still be a function now? This would no longer be a function if you switched what the input and output values would be. Reason being because 2150 is mapped to both 1960 and 1968.